You're on mute, Elina.
Thank you. So, hello to all. In Finland, it's good afternoon. I can see already really nice number of participants joining, so we can start. Welcome to IEA Bioenergy's triannual conference and session Bioenergy's contribution to low carbon energy systems. And I'm really happy to see so many of you joining us. We are already almost 100 people here. To start by introducing myself, my name is Elina Mäki. I am a senior scientist at VTT Technical Research Center of Finland, where I work with topics such as flexibility, system integration, and low carbon energy systems and concepts. I have also led IEA Bioenergy Task 44 since the beginning of this year. The Task 44 is called Flexible Bioenergy and System Integration, and you will hear a lot more about our work during the past 3 years today. I will moderate this session, and as a co-moderator, I have a Task 44 colleague, Jaap Kiel, who is the manager of biomass program at TNO in the Netherlands. You can see also Jaap on your screen. In this session, we will focus on the multiple services and benefits that bioenergy can provide to a low carbon energy systems, both in the transition phase and also in the longer run. And these benefits and services include, for example, different types of flexibility from bioenergy and provision of biogenic CO2 for storage and utilization. We will have today altogether 5 presentations from experts in the field. We have one last minute change in the agenda. So one presentation by Scott McDonald is missing today. We are really sorry for that. That was a last minute change for our agenda, but we have 5 really nice presentations coming. Today, we will hear about expectations on bioenergy, technical possibilities and success factors, and also really interesting examples of services that bioenergy can provide. Then a little bit about practicalities. You can leave us questions at any time. Please write them in the Q&A box. So not in the chat box, that's more to say hello to all, but leave your questions in the Q&A box and you can do it at any time. We will get back to those questions in the end. So Jaap will keep an eye on the questions and guides us through the Q&A session after the presentations. And I also would like to announce that we have a parallel page called wonder.me in use that's provided by Etta Florence, who is taking care of the technicalities of the session. So you should already receive the link in the chat box. And through that link, we can network and continue the discussion of this session already or also after the session. So feel free to join us there after this session. And well, before we go to the first presentation, let's warm up a little bit. So you will soon see the first poll question of this session on your screen. Actually, already now. Thanks, Ernesto. And we hope to hear your opinion on question, what is the most needed service from bioenergy for the energy system post 2050? So now we are looking for a pretty long time scale. And well, I think it would be pretty hard to choose only one, so we let you pick up 2 options. You can take your time to answer. Also during the next presentations, I will show you the results a bit later. So let's now take our first presenter. Ilkka Hannula is a senior analyst at the IEA International Energy Agency, where he is leading the agency's analytical work on renewable energy technologies, focusing on their potential to deliver electricity, heat, and mobility services. Before this position, Ilkka worked at VTT in Finland as my good colleague. And Ilkka is also the former leader of the IEA Bioenergy Task 44. So it's really a pleasure to have Ilkka here. He will set the scene for our session and talk about expectation from energy system transition on bioenergy. So over to you, Ilkka.
Thank you, Elina. I need to change a different mode, but now the taskbar of the...
You may go to display settings and then swap
Yeah,
display.
I go, but the taskbar of the Zoom was on top of it. But now
The second one?
yes, good.
Okay.
You see it in full screen now?
Yes.
Okay, hello everyone. Also on my behalf, thank you, Elina, for the kind introduction, and thank you for the invitation to join here today to share some perspectives from the IEA. I want to start with making a couple of remarks on the COP26 meeting. Our executive director gave his own assessment on the COP26 about 2 weeks ago in a press conference, and I think his assessment was quite a bit more optimistic on the meeting than what we have seen in the media on average. And indeed, there are a number of reasons to also to be positive about the outcomes of the COP26 meetings. In many fronts, progress was made, especially in commitments. Today, we have 90% of the global GDP is under some kind of net zero pledge, which is quite remarkable when we remember that 2 years ago it was 10%. In the meeting, we heard from India a new their own net zero pledge. Then there were over 100 countries signed the global methane pledge, that they plan to limit methane emissions by 30% by 2030, which will have a big impact because methane is such an aggressive greenhouse gas. In collaboration, whatever the today's geopolitical issues are, the two largest economies, US and China, still made a joint declaration to work together on climate change. Then there's the Just Energy Transition partnership with South Africa that might become a blueprint for how to phase out coal in developing countries. There were some clarity on rules, system how to raise commitments each year, some limited progress on finance, and then some things that I want to mention that I think are relevant for bioenergy. The coal phase down, whether it's phase down or phase out, still I think it will have impact on bioenergy in the form of co-firing potential. Then there was the Glasgow's leaders' declaration on forest and land use, which aim to halt deforestation and land degradation by 2030 and work towards sustainable production of commodities from these resources. Glasgow breakthrough on agriculture was to make climate-friendly and sustainable agriculture commonplace everywhere in 2030. And then there was the new announcement of the new integrated biorefineries mission that will funnel funding and spur cooperation on this topic. So a number of reasons to also to feel positive. Now, pledges are there, but targets alone are not enough, of course. So we are still, despite many meetings, we still have not witnessed a sustained decline emissions. Indeed, the IEA now predicts that global CO2 emissions are set to increase by 5% this year as demand for coal, oil, and gas rebounds with the economy. So clearly now it's time also now to start implementing those ambitious pledges. And as a part of that, the IEA published this May its net zero emissions 2050 roadmap, with the specific aim that, because the long-term targets are important, but it's very difficult to say what should we do today or tomorrow in terms of policy so that we would know that we are on track with our ambitious long-term goals. So this roadmap, the first global net zero emissions roadmap, has taken this long-term view and break it down into near-term measurable milestones that can be considered by policymakers, so that if you implement these, then you know that you are on track with your long-term goals. The roadmap includes over 400 milestones. Here, some of the most important ones are written out. I want to highlight some things here that I think are especially interesting and important from bioenergy perspective, like having half of aviation fuels sustainable by 2040, having net zero electricity sector globally by 2040, excuse me, and capturing 4 gigatons of CO2 already at 2035. Each of these a big feat on its own, taken together a complete transformation of the energy sector. So looking more closely, the contribution of bioenergy in the roadmap, we see a number of things in this figure. One of them is that bioenergy contributes to all relevant energy sectors: electricity, industry, heat, and transport. There are the total use of modern bioenergy increases fourfold. So from about 25 exajoules today to about 100 exajoules in 2050. Fourfold increase, while at the same time, the traditional use of biomass, which is significant today, mostly this means collection of fuel wood for cooking purposes in developing countries, which is unsustainable and polluting. In the roadmap, this is phased out completely during this decade. So the unsustainable part is phased out, and the modern sustainable part quadruples in the next 3 decades. So that in 2050, bioenergy meets almost 20% of total energy needs and becomes the second largest source of energy supply, second only to solar. So obviously, bioenergy plays a crucial role in the net zero emissions roadmap. Looking more closely to fuels, we see significant expansion both on gaseous and liquid. So the gaseous side, biogas expands, but especially in upgraded form, as biomethane has witnesses a significant expansion. In liquid biofuels side, advanced fuels grow and expand rapidly over the next decade, so that they go from less than 1% of total biofuel supply in 2020 to almost 45% in 2030, and then eventually 90% in mid-century. And increasingly are going to be produced in connection with CCUS. So you see the shaded part of the bars here, they kind of illustrate the share of production that is connected with CCUS. Also on electricity, bioenergy increases. Here you can see that it happens both in terms of absolute generation, but also as share of electricity generation, which is significant because the electricity production expands significantly in the roadmap, but still bioenergy grows more than the total supply, so becoming about 5% of energy generation by 2050. But bioenergy doesn't, in the electricity system, does not contribute only through low carbon energy or low carbon electricity, but also it provides other services. So as you can see here, a case study for China on the right-hand side, the 2060 situation. Bioenergy not only provides energy, but it provides stability, it provides flexibility and capacity adequacy. So it is this unique feature of bioenergy that it can address kind of all the services needed in the power system, whereas some other, although critical technologies are more limited into some services than bioenergy. So very important part of the story here. And then I want to finish off by focusing on this capture part. So bioenergy with carbon capture, utilization, and storage. By 2050, the roadmap sees about 8 gigatons, almost 8 gigatons of carbon dioxide captured per year. That comes from diverse range of sources, mostly from industrial emissions and from fossil fuels, but about 1/3 of the CO2 is biogenic and atmospheric in nature. And of that, about 80% is stored, and then the rest, about 20%, is then utilized for products. So I think a really interesting part, again, coming to the front as a kind of as a byproduct of net zero emissions pledges, is that you cannot achieve without negative emissions, and bioenergy will play an important role in that respect as well. All right, so I want to give some concluding remarks here. So as shown in the roadmap figure, I think it tells quite convincingly that to reach net zero globally by 2050 is nothing short of a revolution, unprecedented transformation in the way we produce, transport, and use energy globally. On the low carbon fuel side, liquid biofuels, biomethane, and also hydrogen-derived fuels. In the roadmap, they help to decarbonize sectors where direct electrification is challenging and costly. And when we have an energy mix that is dominated more and more by wind and solar, sustainable bioenergy plays a major role there in flexible energy generation, in industry, in transport, and is increasingly used in connection with CCUS. We just published a few weeks ago our latest edition of the Tracking Clean Energy Progress. And from there, you can see when you contrast the current development with the net zero demand, bioenergy is not on track. There are many technologies that are not on track with the net zero emissions, but bioenergy is one of them. So a strong boost for bioenergy is needed to be on track. We need to both deploy everything we have commercially available today at increasing rate, but then importantly, also for bioenergy, we need to develop new technologies during this decade so that they will be available commercially in the 30s and the 40s, then to shoulder and take the responsibility of further carbon emission reductions when we are chasing that net zero. Thank you very much.
Thanks a lot, Ilkka, for this overall picture and providing the IEA perspectives. I can see questions coming for you, and we will take them in the end after the presentations. The audience, just provide all the questions through the Q&A box, just as a reminder if you were not present in the beginning of the session. And this presentation leads us straight away to our second presentation, which is a little bit a bit from a different angle of the story. So it's titled Bioenergy Options to Serve Renewable Energy System. So now we will hear about the technical options. And the presentation is given by Tilman Schildhauer, who is a senior scientist in thermochemical processes and scientific lead in methanation and industrial Power-to-X at Paul Scherrer Institute in Switzerland. So the floor is yours, Tilman.
Okay, thank you very much for the kind introduction, Elina. So, can you see it now the right way?
Yes.
Okay, fantastic. So, actually my task for the next 12 minutes or so is actually to walk you through the technical options which we have to use bioenergy in a flexible way to actually serve the energy system in an even better way than it is today. That a little bit shows you the landscape which we are talking about. So we start actually, we have actually feedstock from biomass. One is dry biomass, so mainly wood or straw or things like that. And there's wet biomass. And these actually already have some differentiation because dry biomass you somehow can store without it's decaying. And wet biomass usually has a problem that it starts decaying by itself and producing CO2 or maybe methane. So we have to do something about it. And on the other side, we see all these appliances in the system. Where you actually produce heat and electricity, you might use bioenergy for transport mobility, but maybe also for the production of chemicals. And at the end also, and Ilka already mentioned that, we could use biogenic CO2 for negative emissions. And on the way from the left, from the feedstock to the applications, we actually see we have intermediates. So these are materials which we usually cannot store so easily. Typical example would be biogas, pyrolysis oil if it is not stabilized, and product gas from gasification. So these, to store these is a little bit complex. Also, the transportation is not that easy. Infrastructure is not available. While on the other hand, for the energy carriers, we actually have an infrastructure, we can store them, and we know how to use them. So there will be methane, there will be liquid fuels, but also very traditional wood pellets or chips, biocoal, but also stabilized pyrolysis oil. Now, this flexibility of this bioenergy actually has two dimensions. One is the short-term flexibility, and this actually connects immediately to the electricity production by renewables, so especially by wind power or photovoltaic electricity production. So if there's a supply and the demand do not match, then actually biomass could actually help two ways. One is producing electricity when it's needed and there's not enough supplied, or taking up electricity which cannot be used at a specific point where it's produced and at this time. So that is what we call the short-term flexibilities, being positive or negative. The other one is long-term flexibility, and that means we actually convert energy into a form where we can transport it or store it. So we actually get a larger spatial or temporal availability of this energy. And what we actually recognize is there are existing technologies which are used today, and in the next slides you will see them indicated as green arrows. There are emergent technologies, those which have been demonstrated successfully on the technical level, so they work, but at the moment they are not so much applied because we are lacking business cases. And then we have with the red arrows, you will see the ones which are still under development, so actually below pilot scale. Let's start a little bit with the wet biomass. The very first thing which we do with wet biomass is producing biogas. So this is absolutely state of the art. There are 10,000 of plants. All of them work, so they could work on residues from agriculture or from food processing, but also in wastewater treatment plants. And these usually have storage capacity of in the range of hours. So they give some flexibility here, which is also important then later for the use. And there is two ways to use that one. One is using the long-term flexibility. So if you produce an energy carrier for which we have a storage and transport infrastructure, so that would be methane, or if you liquefy it, then LNG. And that is actually by separating the CO2 from the biogas. Also, this is a very well-known and good accepted and very often used technology. Also being very, very flexible with time. You can start and stop these plants relatively fast. And the same actually holds for always using actually biogas or the upgraded biomethane in combined heat and power plants. Again, completely state-of-the-art, thousands of plants everywhere. They can ramp up and down in very short time and with very large load range, which actually allows them to be very strong on this short-term flexibility, so supplying peak electricity when it's needed. And on the other picture, you can also see we could use it as LNG as trucks for long distance transport. So these are technologies that are well known. What is a little bit developing is using biogas for power to gas. So we actually use the CO2 part of the biogas to store hydrogen in form of methane. So we convert hydrogen, which is produced from renewable electricity, which cannot be used otherwise. We store it by converting it to methane, and then we use the methane infrastructure. And this technology we technically has been shown in several plants. So we know there are plants which work in megawatt scale. So we are here TL7, 8. And this is a technology which is on the onset of being used also in commercially, but at the moment there are very few plants. What you usually have is when the plant is warm, then you can start up within 20 minutes. most of them actually are able to inject the methane into the grid within 10 minutes or sometimes even 5. So they're really nice, and depending on the technology, also here have a very strong load range. Some of them can work with very little hydrogen, others start at 20%, but generally a very flexible technology to take up electricity, so to offer negative ancillary services on the one side, and converting biogas, which cannot be stored, into an energy carrier which can be stored and transported. And the last thing which actually comes out, both from the upgrading of the biogas, but also is in the use in the CHP. In principle, there is biogenic CO2, which you could capture and use for negative emissions. This is actually not so much done so far and more under development, but clearly an option to reach net zero emissions. And in future, it will be most probably a kind of a balance where we use the biogas for negative ancillary service of power to gas in summer, but in winter, when no hydrogen is available, we might go and then separate the CO2 for negative emissions. Let's have a look on the wood side. There, the first thing we can do is actually forming chips or pellets and using it in, again, in combined heat and power plants, or to make a little deviation by producing product gas by gasification. Again, many plants in small scale. If you have a combustion or a gasification, then the startup time is not that fast. It's between 1 hour, 1 day, depending on the size. Load range is moderate. But again, like in the biogas plants, the engine or the organic Rankine cycle, which actually uses the heat or the chemical energy input, actually can change very fast the load, and again can jump in for flexible peak generation, or actually turning down electricity production into part load if too much electricity is in the grid. So again, this is a very well-known and well-accepted technology which could be used for short-term flexibility. Generally, this way over gasification is also possible in a large scale. So we know that a couple of these plants, here again, because of the size, gasification most probably takes nearly a day, but the gas engine itself is very flexible. Something which emerges now lately is actually pyrolysis of wood and similar feedstock. So where the pyrolysis as such is more or less commercial. So there we see the first plants being built at several places. As I said before, the pyrolysis oil itself should be used relatively fast because it has this tendency to change chemically. But in principle, it could be stabilized with hydrogen. This is something which has been shown in many experiments, and actually technology is very close to what we know from refineries. So I think once the demo, the business case is there, that will be applied also many places, because it's another way to actually get, let's say, decentral biomass into an energy carrier which can be easily transported. And now the things which are a little bit more under development is actually using the gasification gas and then producing fuels, so being gaseous fuels like methane or even liquid fuels. And we see now there's no green anymore. This is mainly yellow. So it means we have the first plants which showed it in demo scale, but we also see that there's still a long way has to be done. And principally, like in the biogas case, there would be an option to actually add hydrogen to the system or taking out CO2 for negative emissions. So use it flexibly, and even maybe changing that behavior depending on the electricity supply or the electricity price. So when electricity is cheap, you add hydrogen, you produce more of the fuels and getting actually all the carbon into your product. And if there's not no cheap electricity, you maybe do not add hydrogen, and then you have actually to separate CO2 because it's part of it's a coupled product of all these fuels. And then you could actually capture the CO2 and use it for negative emissions. And again, like in the biogas case, this negative emission pathway is not yet developed so far, because so far the incentives were not there. So if you put all that on top of each other, we see actually there's an enormous network of flexibility options for bioenergy. And I think the future energy system can use all of them. But as I said before, some of them are more applied than others, and that actually now we actually distribute them into this matrix, and we see biogas upgrading is the only technology which offers long-term flexibility and which is done in large scale. While actually this peak generation we see at many places is based on biogas and also on dry biomass, and we see many technologies which are coming up only slowly, which have been demonstrated but which are not so used so far. Many of them based on wood gasification. The pyrolysis oil is there. Yeah, that is something which can come up. And we see a couple of technologies which I didn't show so in the previous slides, hydrothermal processes which are actually able to get even wet biomass on the same process routes like dry biomass, chemicals from biomass. So these are things which come up. Maybe also using SOFCs as combined heat and power plants. Coming to my last slide, so what we have seen is there are many technologies. They have been demonstrated successfully, so they work. What we see is business cases which work beside actually the combustion of wood, which always worked since ever. The business cases which work are the ones which start from waste streams, and this is usually biogas. And then all the technologies which actually can offer peak electricity production, because already in many countries there is some support scheme there or some incentives to do so. For wood, it's a little bit difficult to actually go to these more advanced technologies, because the combustion of wood is always a potential alternative, which at many places also makes sense if you anyway need heat in the first place. So you have to really look careful where you use the wood. Flexible hydrogen addition is something which will be more of interest in future. And this actually is in balance with the use of the CO2 for the negative emissions which you can might need in future. And where actually bioenergy is one of the most important sources for. And yeah, what we have seen is you have all these technology options. They have many advantages, but at the moment, most of them are not valued in a way that you have incentives to really do so. And with that, I would like to thank you for your attention and all my technical colleagues from the other tasks which supported us to produce this technology report, which you actually can download from the IA homepage. Thank you very much.
Thank you so much, Tilman, for this very comprehensive overview of the technical possibilities. And I also just left a link to the report to the chat box, so you can find it there directly. Before the next presentation, let's see the results of our first poll question. So we asked you, what is the most needed services from bioenergy for the energy system post 2050? And the winner with 55% of votes seems to be bioenergy together with hydrogen for hard to decarbonize sectors. And that's not very surprising, because as Tilman also highlighted, there is a lot of possible synergies with hydrogen economy and bioenergy. The second most votes went to biogenic CO2 for storage and to provide on-demand dispatchable energy production based on storable fuels. So those are, of course, very much the strengths of bioenergy. And the peak load provision likely becomes as a first step, or it's already appearing in the energy transition. And let's now take the second poll question, and that is what type of flexibility provided by bioenergy is most important to your opinion when energy transition accelerates? So while the first poll concerned longer time span, now we talk about shorter term energy transition phase, and we are talking in particular about bioenergy's flexibility options. And again, you can take your time to answer. We will get back to the results later. And now we will move to our first exemplary case. I'm really happy to introduce Alexander Krautz from Germany as our next speaker. Alexander is head of business development at Next Kraftwerke, where he is responsible for development of business cases based on analyzing and evaluating regulatory frameworks and market potentials of new technologies. Key subjects of his work are digital and aggregation energy business, virtual power plant services, and sustainable energy products. Previously, he also worked at the German Biomass Research Center, DBFZ. Alexander will talk about bioenergy in a virtual power plant, dispatch, and ancillary services to stabilize the power grid. So over to you, Alex.
Yeah, thank you, Elena, for the nice introduction. Yeah, Tilman talked about short-term and long-term flexibility. My focus will be on the short-term flexibility and how we can use this flexibility on electricity markets. Next Kraftwerk is one of the biggest VPP operator worldwide, and we have around 3,400 bioenergy plants under management. So as market participants, here are some short numbers about our company. In total, we have around 12,000 assets under management with an overall capacity of around 10 gigawatts. That's around 10 nuclear power plants. So the assets are located in Germany, Belgium, Netherlands, France, Italy, Switzerland, Austria, and Poland. We are active there in different markets, in the ancillary service market, control reserve markets, and at the wholesale market. As flexibility provider, we have a pre-qualified capacity of around 75 megawatt in the FCR. FCR is a primary reserve. To give you an image, the overall market size in Germany of the FCR market is 580 megawatts, and the most of the FCR pre-qualified capacity is from bioenergy plants. So we can provide FCR with bioenergy plants. And we are also active in the AFRR market. There we have around 1 gigawatt pre-qualified capacity. There is a market size of around 2 gigawatt, and the market size of the MFRR is 1 gigawatt, and there we have a pre-qualified capacity of 1.7 gigawatts, so more than the market size is. So in Germany, we manage around each third bioenergy plant, and so the German market is a special market. We have a lot of biogas plants, and there is in the German Renewable Energy Source Act for us good subsidy. So there is subsidy for further investment into additional flexibility. So, but I also want to talk a little bit about virtual power plants, and a lot of people talk about virtual power plants, and there are a lot of different definitions what a virtual power plant is and what a virtual power plant not is. For me, it's a virtual power plant system which can aggregate decentralized assets. So, and when I say decentralized assets, then I talk about asset size from around 100 kilowatts to 20 megawatt. Such a system has a control center which can monitor and control all data. The system is fully automated. The system is redundant. So we have different server locations. If there is one server down, then a second server can take over the work for the system. The system has a high performance. So we had discussions with some colleagues from Asia, and they said, oh, we also have a VPP. We manage around 20 assets with them. So we have 12,000 under management. What is really important, we need high security standards. So in these times, we have a lot of security problems in our virtual systems, and but our system is secure because we are fully independent. And we are not in the open internet. It's a closed system, and because of that, we fulfill the highest security requirements. And we are also a certified critical infrastructure in Germany. So a VPP has to take over market and system responsibility, like a conventional power plant. Some short words to the wholesale market. That is where the electricity is traded. But it is not one market. A lot of people say the electricity market, but we have the long-term market, we have the day-ahead market, we have the intraday market. There are a lot of markets where you can trade your electricity. And at this market, each participant has a balancing group and is responsible to balance the balancing group. If you have a wrong forecast, or there are bigger maintenance works or something like that, then you have to secure that your balancing group is balanced. So you have to make a trade, or you have to balance it out with flexible assets. So there are different possibilities. On the other hand, we have the ancillary services like control reserve, which are provided to the grid operator to stabilize the grid frequencies. So we have here two different markets, more or less. The transition of the energy system to more renewables also requires a transition of the market system. In Germany, we have seen that as the share of renewable energies has increased, the need for flexibility has not increased. Why was that so? The reason for this was that new short-term trading opportunities were introduced. So you can see on this slide that over the past years, the volume in the intraday trades increased. So, and the best flexibility is the one you do not need. So, and this is one important message. So everybody talk about to provide flexibility, but there are a lot of opportunities to reduce the demand of flexibility. But what is the impact of fluctuating renewables to the market? So everybody talk about wind and PV. And in times with a high share of PV, for example, we can see a direct impact to the market price. The higher the share of PV, the greater the impact on the price. The demand for flexibility increase and offers new possibility for bioenergy. So in this example, you can see that we have negative prices on the market. So, and so this means in a system where you have negative prices, you have to pay for your electricity. So it's a penalty, more or less. So, and if you can switch your asset off, then you earn more or less money, or you lose not so much money. So, and but important for flexible assets are price differences. So, and in the last weeks, especially, we saw very high increase of the overall market price, but also we saw very high price differences from time to time. And these are very good possibilities for bioenergy, for flexible bioenergy assets. In our VPP, we calculate for each single asset under consideration of the individual restrictions, the best schedule. So it's a single asset optimization. Compared to this, if we talk about ancillary services, then we talk about a pool concept. So to provide ancillary services to the grid operator, we have a tender. We have a tender. Such a pool concept is not easy to manage, but a VPP gives you the possibility. So we have a daily tender, and we have to guarantee availability of 100% to the grid operators. So we need some assets in the back, and such a pool concept can only provide with a VPP, because you need a fully automated system, and you provide a capacity, but also the possibility for the activation. So here below you can see how the FCR, AFRR, and MFRR market is structured in Germany and in the most part of Europe. So in other countries there are similar products, but with a little bit other restrictions. This slide shall give you an image how the activation of an AFRR call works. After the call of the TSO, the system selects the best assets and activate them. If one asset is not available, the system activates the next one. The TSOs gave us the feedback that the performance of our pool is better than the performance of a conventional power plant. So you can see it here. So at the top, we have activated 376 assets all over Germany, fully automated. And after the call ends, the system has to bring all assets back to the baseline. And here, a good performance is required. So, and yeah. The requirements and good performance, as I said, are very important to provide flexibility. And here is an example from different assets. So not every plant is suitable for a flexible operation. This asset has a very good performance. It looks not flexible, but it is very flexible because it provides control reserve more or less perfect. So if we call it, the reaction time is very fast, RAM speed is very good, and if the call ends, then the asset come perfectly back to the baseline. Compared to this asset below has more or less a bad performance. So sometimes you have downtimes and so on. And with this asset, it's hard to provide flexibility. But because there are the deviations from the baseline are too high. You cannot calculate them, and ramp speed, for example, is also very bad. So what is important for providing flexibility? Important is a good plant management, and it's important that you have a planning capability, so and that you can control it. So if we look to older assets, then it's sometimes hard to control them or to plan the asset. And as I said, what also important is that we have a fast reaction time, good ramp speed, and high performance quality. And what we also need to provide flexibility with a pool of assets or with a VPP is a fully automated system. So because of that, we also have a fully automated customer portal. We have a web solution, we have an app solution, so the customer can get push messages, so that the customer has the possibility to manage and remote monitor the assets fully digital. So your colleagues can sit behind you and see how his asset somewhere all over the world works. So this brings us to a new situation, and this is for some of our customers very important. So because not every customer is 24/7 at the asset. So my conclusion, so if we look to the next decade, the demand for flexibility at the wholesale market and the ancillary service markets will increase. To participate in the market, market opening and development of wholesale markets and ancillary service markets are required. So in a lot of countries, there is not the possibility to provide flexibility with bioenergy assets. In some countries, there is no real wholesale market, and in other countries, there is it not allowed to pool assets to provide ancillary services. The VPP gives bioenergy plants the possibility to participate in such markets, and with a VPP, you can control these assets very good, and you can take over function of the conventional power plants. But a professional plant management and good heat concepts are necessary for efficient operation of flexible bioenergy plants. Thank you.
Thanks a lot for this, Alexander. As I announced in the beginning of the session, our next speaker, Scott McDonald, had to cancel his presentation. So we will jump to the next one, which is given by Christiana Hennig. She will integrate two different services from bioenergy and talk both about bio-CCS and bioenergy flexibility, finding the balance between those two. Christiane is a senior research associate in the Department of Biomass in the Energy System at the German Biomass Research Center, DBFZ. She is engaged in research projects in the fields of energy transition and strategies promoting the use of biomass towards a circular bioeconomy and low-carbon society. Within IA Bioenergy, she is a member of Task 44 on flexible bioenergy and system integration and co-task leader of Task 40 on deployment of bio-based value chains. Please, Christiane, the floor is yours.
Thank you, Elina, also for this lengthy introduction of myself. So there are no further words needed. Thank you for this. And hello also to the whole audience and for joining the session. So my first question would be also again to everyone, also to Elina, if you can see my screen.
We can, but maybe you would like
And the
to
presenter
put it
mode.
in the presenter mode.
Okay, so.
Perfect.
Okay, thank you. So with this presentation, I want to share an outline and also show you some preliminary findings of a work that is related to strategic intertask projects within IEA Bioenergy. It's on BECCS deployment, and this subtopic here, bio-CCS and bioenergy flexibility, finding the balance, is a subtopic which I worked on, or I'm still working on, in collaboration with my colleague Ola Olsen from Stockholm Environment Institute, and he's also part of Bioenergy Task 40. This project overall from bio-CCS and BECCS deployment is led by Task 40 and in collaboration with Task 45, which is sustainability, then of course Task 44, which is the flexibility, and there's also Task 36. They are taking care of waste and the circular economy. So where did we start to actually look into these aspects of bio-CCS and flexibility? As you heard in the introduction very nicely by Ilka, the question is if we have these different mitigation scenarios and also the pathways and their corresponding measures to stay well below the 2 degrees of global warming, how to actually achieve this. So there are many already scenarios out there and pathways presented by IPCC, but also by the IEA Net Zero Roadmap, which was presented by Ilka. You see here the key pillars that have been identified that will help to decarbonize the global energy system. And especially if you look at the 4 ones listed below, you see these are 4 areas where bioenergy strongly comes in. So here we have strongly the bioenergy perspective, and we can see that bioenergy can support these 4 elements and helping to decarbonize. This can happen either that you have a direct substitution of fossil fuels, or that bioenergy can provide really valuable energy services, and in the end also climate system services. Our research with that focuses mainly on the system perspective, which is also the core of IEA Bioenergy Task 40 and IEA Bioenergy Task 44. And here we look at these 2 services. We were referring to flexible bioenergy more as an energy or bioenergy service, and bio-CCS is overall more a climate system service, which can be provided by the energy sector. So the question that we had, or that we still have, is how to actually implement and bring these bio-CCS and flexible energy into a broader and faster deployment. So we were really looking at the deployment when it actually we're saying we want to have this more happen in our energy system. And the thing that I added here with if required refers to, so if we have a pathway that actually asks for the service of bio-CCS and flexible bioenergy. But of course, most of the integrated assessment models and also most of the scenarios also within the IPCC have a close link to bio-CCS. So as I mentioned, this is really important to say that whatever I present now is still work in progress. And we're really happy that we have the platform here today to present what we have already achieved and what our thoughts are, and maybe to have later on also a discussion on this. So also the input from the audience we see as really valuable aspect to proceed with our research. And the idea is to have a publication in the first quarter of next year. So why is this important? Why we were doing this, or are we doing this? So as I said, bio-CCS and flexibility are already considered as the most important characteristics that will help to achieve a low carbon energy system. And we have now to find out what happens actually if we implement them, and maybe implement them at the same time. So at the same time meaning maybe with the same facility, or at the same time having various facilities that are supplying bioenergy flexibility and various facilities that are providing CCS. So what does it mean for the existing bioenergy system? And there we want to find out how can we use this more in synergies than in rather than in trade-offs. Before going into our more broader methodology, it's maybe really worthwhile again to look at both bio-CCS and also at flexibility independently. So when looking at bio-CCS, as mentioned, it is really in most of the models and also presented by Ilka, one of the main discussed carbon dioxide removal technology. So here I used one of the tables that is included in the IEA roadmap net zero emissions by 2050. So you can see here that bio-CCS has a dedicated share in here. So it's going to a main part to contribute on this pathway and to provide negative emissions. So this is only one example of many where this appears in this manner. What is interesting to know on bio-CCS, it can actually be implemented anywhere where there is biogenic CO2 or CO2 emissions. So this is really something that is good to know. Of course, what would be important is that the source is rich in these CO2 emissions, so we can achieve a high capture rate. What else is important is a broad range of sectors can be used for this. So it's not only when you think of electricity, but of course it could be also in other industrial facilities or heat and power or in pulp and paper mills. So it's much broader where CCS could come in. Now having a look independently at flexible bioenergy. So at the beginning and in some literature, flexible bioenergy is mainly related to the electricity system to provide grid stability there and to integrate wind and solar power. So this is the main understanding or what we see that is often related to. However, if we go into this transformation of the energy system, more sectors would be needed where we can use flexible bioenergy. And it's possible to also use flexible bioenergy much broader. This you could see very nicely by the presentation that you were seeing in the presentation before, where you could see that there are different outputs, different inputs that are available. So it's much broader than this. And if you see this, then we can think in flexibility in terms of inputs. So as presented, it could be wet or dry inputs, but also in outputs. So seeing different energy carriers, also usage in different systems, for example, also for transportation. So it's not purely electricity. And it is something that was taken on within the work of Bioenergy Task 44, that here the definition got broadened. And I think this is very important also then for the further understanding of our research, that here we see a definition where it's related to that bioenergy system that can provide multiple services and benefits to the energy system. So it's much broader, it's the energy system. And we have multiple options to provide flexibility there. The whole definition you can also access via the webpage from Task 44. So it's available there for you to read and have a look. And I really can recommend this because there are also examples given that really give an idea how much more flexible bioenergy can do. So after having these independent, after having these independent looks at bio-CCS and flexibility, we want to come now to have a first look when combining them. So what do we see when we have bio-CCS and flexible bioenergy? What first came to our mind, or what we figured out, was that they're implemented at a different speed. At different speed, we're relating to that we can see in some countries that flexible bioenergy is already in place. And as you could hear from this presentation from Alexander, there are already really strong players who can provide these flexible bioenergy services in relation to grid stability and integrating solar and wind power. On the other hand, within the bio-CCC arena, we could see that all these serious considerations happened in the last 5 years, how to actually implement this. So we're talking about implementing. It is not that real life testing already has taken place on a large scale. So this brings us to the second point and main challenge, that we are still with bio-CCS at more pilot, and we have to bring it to full scale. And when doing so, we really have to see what happens when we add CCS to existing chains, to existing bio-based chains that have already a certain output, have already a certain mode of operandi, and maybe are running already flexible. So the goal would be to see, when we are bringing in CCS and combining it with flexibility, how can we make the most out of the benefit that CCS has in terms of climate change mitigation, without kind of bringing any drawbacks to the energy system. And here I have the questions that are addressed. I don't want to go in detail because I think I mentioned it many times already before. So the research question that we were having is, how do bio-CCS and flexibility interact? So this is the underlying main question to be explored. Since this is now a really broad field to start, and we were also saying there are many sectors that can be touched upon, we were making use of already existing case studies. So within this Intertask project, deployment of Becker's value chain, which I mentioned before, there were already happening research activities. So there are already publications out there on certain bioenergy installations, but also other industries, for example, as listed here, cement. And we were using these case studies as a kickstart to go from there. If we take these ones as the most developed or most thought through bio-CCS applications that we are seeing, and then we see what would happen if those ones are taking and combine them with flexibility, or what does it mean, flexibility, for these chains. When you're interested, also this publication on the deployment of Becker's value chains and also all the case studies, they're also available on the website, either on the IEA Bioenergy Task 40 website or on the general IEA Bioenergy website. So you can have a look there, what is actually the current status of knowledge. So this brings me to the preliminary findings, or our understanding, what we see, what happens when we bring flexibility, especially flexible bioenergy, together with CCS. So the first important and good message is, from a technological point of view, this is definitely possible to have this combination. However, it could be that when you combine flexibility with CCS, that you maybe don't have the amount of CCS or the amount of a capture rate per one installation when you also run flexible, because then you of course cannot run in base load, so you don't have a high point source for CO2. And this has to be taken into account when looking at different options. So to decide for, okay, if I have CCS and combine with flexibility, then maybe I can find a better optimum for both sides, but in total, I maybe have lower CCS and maybe need an additional plant that needs then CCS installed. And in this relation, we also found out that there is already some research ongoing, how this flexibility combining CCS can be done more smoothly, or even to bypass this issue that I was just mentioning. So maybe there are even possibilities to kind of find really a good optimum of both of these applications. Furthermore, what we saw so far is that when you decide to run flexible, then of course you will have an incentive scheme most likely in place, or you will get some other rewards for providing this flexibility in some of the countries that have this flexible bioenergy in place. And on the other hand, maybe you get some reward from the carbon dioxide removal. So these would be two independent incomes. And the question is, how would they relate to each other? And this carbon dioxide removal at the moment is not a revenue per se by a support system, but for example, if you then not only think about CCS or maybe also CCU, then maybe you can generate a revenue by providing this utilization services. So the question is, how would then an operator decide, or is there any question to decide for? And with this respect, bio-CCS is important for the climate system, and flexible bioenergy is per se more important to the energy system. So the question is, when we have now more BECCS, what would happen then to the energy system? And this is more a side note, because actually we are not only looking at CCS in this study, but also at CCU. However, to the timing that we're having here today, we decided not to present all the input also on CCU, but also for CCU, we're doing the same considerations. And for example, when you look at CCU pathways or the carbon capture and utilization, there, when you have already an established concept or you have a business model, then you maybe need constant CO2 capture. So this is something that has to be in mind when also then maybe having a more flexible operation. With the next slide, I want to show you what will be our ultimate goal. So in the end, we really would strive for developing an assessment metrics. Here today, I present you just an example, electricity sector. And again, this is work in progress. And we would then have an assessment metrics having all the sectors. So you don't only have electricity sector, but you will have all the other sectors that I was telling you as case studies beforehand. So combined heat and power, waste to energy, and we're doing the same analysis for all of them. And we will look independently, first of all, both in the bio-CCS and CCU world, and then in the flexibility world, and then we want to combine them and give information what would happen if you combine them. So the question that we're having with the bio-CCS, what is very important is, can you do actually both CCS and CCU, so utilizing and the sequestration? And how important is it in this respective sector, here at electricity, to have bio-CCS especially? So there are some hard to abate sectors where it is a must, and then we really have to see CCS implemented. And here it's rather to say nice to have. So you will have a good capture rate, but it's a nice to have, but maybe not a need. So this will help to know when you go to flexibility aspects, if you run flexibly, how much you have to maybe take care of CCS. And in this case, we were here then referring to flexibility aspects, both input and output as well. So not only the grid stability, so not only the integration part, but also on possible flexibility on the input feedstock and the output product side. And in the end, we then summarize if there are synergies or maybe challenges that occur. And here's an example. You see again what I listed before. If you run for CCU, then maybe you need a constant rate. And this assessment metrics is then addressed to decision makers. So they have something they can work with when they really finally are going to implement one of the pathways for a world well below 2 degrees. And I'm not leaving here without having an outlook because all this work that we're doing already brought so many new questions that we're not able to cover within this sub-project. So I just want to give you some bits on our outlook and maybe questions that we're having for future research. So the thing that we are seeing as very important is on the policy side. So when you see these outlook bullet points that I listed here, they're all addressed on to address the decision makers and refer to the policy side. So what we see is that the current support measures, for example, when you have flexible bioenergy in place in some countries, they use incentive schemes based on premiums. They would need a revision if we are saying there are other policies that are coming in that reward, for example, the carbon dioxide removal. So when they come in, then it's the question how to incentivize both in an optimal way. So this is something really challenging that we see, but something that is required to have a really good use of the resource bioenergy. So, and this brings us to one of the main questions that we're having on the bio-CCS side, that we need a policy design for this. So it's not only that we are only most of the cases in the pilot scale of the CCS applications, but we also would then need a policy design. So there is an incentive for actually to make it happen if we decide for bio-CCS as an option to generate negative emissions. So, and this was all from the study so far. And yeah, I hope there are further on questions on this, and of course, sort of a discussion, even if it's via typing. And if you have any questions or remarks, you can see the contact details here from Ola Olsen, my colleague, and myself, and feel free to contact us. Thank you, and then I hand back to Elina.
Thanks a lot, Christiane. And as we heard, it's not very straightforward how to really balance between different bioenergy services. And I guess it might be also very system dependent. And I'm really looking forward to continue this in the Q&A session. Before that, we have our last presentation. It will be given by Professor Daniela Tren from Germany. And it's about bioenergy in a well below 2-degree world, expectations and success factors for long-term evolution. And Daniela is head of Bioenergy Systems Department at German Biomass Research Center, DBFZ. And she is also the head of the Bioenergy Department at the Helmholtz Center for Environmental Research in Leipzig. And Daniela is also the co-lead of Task 44. So the floor is yours, Daniela.
Thank you very much, Elina. And with this presentation, bioenergy in a well below 2 degrees world, expectations and success factors for low carbon energy system. Yeah, I would like to bundle and bring together the different aspects we have heard in the last 1.25 hours. So, climate change is ongoing, and a well below 2 degree world is possible, but following the assessments of IPCC, we have not more than 10 years to act. And this is a global perspective. Here you see we have already climate change and temperature increase all over the world. 10 years to sustainability, decarbonize the energy system, but also other sectors like buildings, chemistry, etc. What is expected from bioenergy here? It is provided from biomass, and again, the global view, most of the land is already used. So when comparing the global biomass harvest for everything, for all kinds of purposes, for food, feed, and materials, we talk about 200 exajoules today. And when comparing this with the current use of fossil fuels, we talk about 450 exajoules. So it is clear the relevant success factors for bioenergies are increasing efficiency, cascading, and synergy in the implementation of renewable energy system. And we heard a lot about from Ilka already about the global perspective here. How can those synergies can look like in the shorter term and also down to earth? First of all, we need sustainable feedstock as a starting point, and of course also modern bioenergy. Ilka talked already about it. Sustainable resource means much more residues and waste from cascading uses, and this means also to be flexible for different feedstocks. Second, we also heard a lot about this. We need variable renewables, which come into the system to have a flexible counterpart. And this is the operation flexibility, which is has been given us an example from Alexander. Operation flexibility is mainly around the electricity system. And it is important to point out here to unlock those synergies. It's not only about energy provision technologies, but also about networked information exchange and small control systems. Third, it is important to have storable fuels for application difficult to electrify. For example, we heard from Ilka the aviation field, but there's also the marine sector and some other sectors. And here we talk about product flexibility to produce different biofuels, but maybe also biochemicals. Last but not least, in the last months and years, also hydrogen came into the system, and hydrogen is another storable fuel. And if we consider green hydrogen, renewable green hydrogen, then the question arises how hydrogen and bioenergy interact in the best way. And hydrogen can be made from biomass, but this is more a niche application. When hydrogen in biomass processes, and Tilman showed this nicely, then we can increase yields and have additional options. So this might be the more interesting factor. And our work in task 44, flexible bioenergy, also showed it is not only that we have a wide range of technical options, it is also about very different countries' expectations and prioritization, which is also clear because we have a different starting point, different energy systems, different biomass availability, also different climate strategies. So there's a wide range of priorities also here, and we have summarized this in a country's expectation report, which you can find on the website. However, this is not only about, let's say, future and expectations. We have in some niche flexible solutions integrated already. And this is also an activity we do in task 44, and you'll find them collected in the website. Here we have collected best cases to show what is already in the world. And those best cases collection is still, let's say, ongoing, though you find the first best cases here, but you will see more in the next months. Three very short examples. Here on the left side, you see the Wholesale e-gas commercial plant in Germany. It is about catalytic methanization, where power from gas is on one hand side produced from green hydrogen and then produced together with flexible biogas, depending on the availability of variable renewable energies. In the middle, this is the Muswellbrook plant in Australia, where ethanol and other liquid biofuels food additives and other biochemicals are produced from sugar and from different lignocellulosic material. So this is more about the feedstock and the product flexibility. On the left-hand side, the e-boiler plant was more about the operation flexibility. And again, about operation flexibility is on the example on the right-hand side. This is the liquid wind production facility in Sweden, where about 700 tons of biogenic CO2 are converted with green hydrogen to produce methanol. This plant will start operation in 2.5 years. And we invite you here to read more about those examples on the website, while I now want to go forward and ask the question, how can the implementation of flexible bioenergy be accelerated? Therefore, we have summarized our findings in the discussion papers, also accessible at the Task 44 website. And the conclusion is that we have to develop 5 cornerstones more in detail. First of all, it's about a clear definition. We include for flexibility, feedstock flexibility, operation flexibility, and product flexibility with many positive aspects, and it's still important to get a clearer common understanding of this flexibility. Second, we should have, as fast as possible, multiplication of best cases, and of course, different best cases fit to different countries due to their different support schemes, etc. So, however, there are already interesting niches. There's a need for technology development to bring more options to the market, and critical issues about policy and market conditions. Actually, there are support schemes for flexible bioenergy, not in many countries, but for example, in Germany and also in Italy. And what we see here is, first of all, the flexible provision from bioenergy increases, especially in the electricity market with these support schemes. And second, also, if you look for the climate gas assessment, we see that climate gas emission reduction per unit flexible power from bioenergy is higher than climate gas emission reduction from base load power from bioenergy. So you can, with flexible bioenergy already today, increase your climate gas emission reduction in the current systems. Which brings me to the 5th point, which is very critical, the appropriate consideration in long-term energy system plan. This is necessary also to understand the flexible bioenergy role and the most climate efficient role in the longer term. So far, the majority of energy system models, and especially the not global but more national energy system models, do not have flexible bioenergy integrated, and this needs to be changed to more elaborate the best role here. This is the expectation for the energy system, the 5 cornerstones which are necessary to accelerate the implementation of flexible bioenergy. But we have also heard from Christiana, flexible bioenergy in a well below 2 world will go beyond the energy system, and also negative emission technologies need to be implemented. And also here, let me just stress it is necessary to start in the next decade. And of course, we heard from Ilka, it is necessary to consider different options for negative emissions, nature-based solutions, direct air capture, and bioenergy carbon capture and storage. But when comparing those different options under specific conditions, I'm sorry, here again, this is an example for Germany. We see 2 things. One we do not have a silver bullet to bring reasonable contributions together. It's only possible if we combine the different solutions. However, when it comes to the implementation readiness, so the technical readiness level, which is given here on this example on the right-hand side in black dots, then it's easy to see that only certain options are available already fully market commercial today. And of course, BECCS is in between those options. And if we also look at the net energy provision, which is given here in green circles, and which is very important, especially for the next decade, because green energy, green electricity is still a bottleneck for the energy transition. Then you again see that BECCS is a promising option, especially in the near term. So it is on the one hand side important to start implementation of BECCS option, but it is also to be expected that they will be the first ones which really have a chance to contribute to the market. What is the conclusion? The success factors of bioenergy in a well below 2 degrees world is its integration and flexible bioenergy as an accelerator for the energy system, decarbonization, but we see also 2 more aspects. One is synergies of green hydrogen and bioenergy deployment, which is important but not very well developed yet. And second, we see the deployment of BECCS and BECCS value chains. Christiana has given some flavors of the ongoing work of IEA Bioenergy here. And the question, how can this whole packet serve the climate system in the best way? And this is exactly where the aim of our further work in Task 44 Bioenergy is. It is about on the one hand side, from global approaches and system benefits in general, we heard about this, but down to earth to the best cases, examples, and the necessary market conditions. How to bring those different systems together and how to serve both the global perspective and the down to earth examples for fast implementation of flexible bioenergy and the appropriate consideration in the long term. Thank you very much.
Thank you very much, Daniela. It was a nice summary also of our future work. And now, before we start the Q&A session, let's see the results of the second poll question, where we asked what type of flexibility provided by bioenergy is most important to your opinion when energy transition accelerates. And I will soon let also our presenters comment and tell about their views on this. As we can see here, the first choice, which was about the feedstock flexibility, actually got most votes. But let's give our presenters a little bit time to think about this, and meanwhile we will take our third poll question, which is actually based on Daniela's presentation. And that is, what is the most important next step to unlock the potential of flexible bioenergy? These are actually the same options that Daniela presented as the 5 cornerstones to unlock the potential of flexible bioenergy. So let's see the results a bit later. And again, it's a multiple choice question, so you can pick up two options. But now I would like to hear what our presenters think about what is the most important type of flexibility that bioenergy can serve in the shorter term. So maybe we can start from Ilkka. We can go in the order of of the presentations. What do you think, Ilkka?
Good question. I think the answer recently with colleagues has been that there's always been in this type of question that about the optimal use of bioenergy. There is so much you can do with bioenergy and it's to some extent limited amount. So what is the best option? But I think that discussion has never conversed much. It's still ongoing. And I think given the demands we see on each sector for bioenergy, for all sorts of roles is much higher than we have today. I think the general answer at the moment is that we need everything we can build and we can deploy and develop at the moment. And we don't really, it's not so much about where to focus, but how to just deploy on each application that we can at the moment. So I would kind of avoid the question a little bit in this case. But I think certain type of flexibility is interesting that you would like to perhaps, I like fuels, upgrading it to fuels a bit because then you can use them later on. There is no kind of, if some market, let's say, doesn't need it anymore, but there's plenty of something else that you can kind of shift to another market. It's not, if you have renewable liquid hydrocarbon, I think there will always be a market for that. If it's now going for road transport, it will, if someday we have so much EVs on the road that it's not needed anymore, there's going to be another place to use it. So I think liquid hydrocarbons, if we take this Tillman's extremely broad view on flexibility, it's not just temporal, but all sorts of things. I would say liquid hydrocarbon is an extremely flexible product from biomass.
Thanks. So let's continue to Tillman. What do you think?
Okay, I was a little bit cursing that I have to start after Ilkka because he took already many parts of my answer away, many options, but I'm still happy that I'm the second one because it's very difficult to decide. And actually, mostly it does not even make sense to say it's the one or the other. I agree with Ilkka that we should do many different things. And what I would like to add here, it actually also depends on the local situation. Very often, biomass is a very local resource. And unless you have converted it into something which you can easily transport within the infrastructure, you have also to use it locally. And then it completely depends. I mean, so I'm in Switzerland, we have many of these pumped hydro storage power plants. So we don't need any, we don't need to use biomass to balance out electricity production. We can do that with the lakes. But this is not true for the Netherlands, for example, right? And so we really have to look what is there and what we should do with that. With already existing infrastructure, and I think very often it's a more of a kind of regional answer and not a general answer.
Yes, and in many cases in our task work, we have run to the answer that it's system dependent, and that's why we also need the best practices. Alexander, do you have anything to add?
Oh, yeah. So I agree. It's very local, and so the situation are very different in different countries. So in Germany, we have a lot of biogas plants, and but we support them. And so in other countries, we have a totally other situation. But if we have such plans, we see the possibility to run them very flexible. Yeah, so as I said in my presentation, so we have now technologies to run them flexible. In some countries, we have perhaps the possibility from the asset side, but the market is not at the stage that we can use the flexibility. So it's also a question of the electricity market, but we also have to look to the heat side. So if we talk about Bioenergy, I do not want to talk only about the electricity. We should also keep in mind the usage of the heat, and that we have good heat concepts, and this is also very important. So not only the electricity market.
Yes, that is very important to go beyond that. What about you, Christiane? Any further thoughts?
Yes, I also only would add further thoughts, if this is possible, after Ilka's intro. So also after Tillmann's comment, what immediately also came to my mind is, since it's a scarce resource and a regional resource, then we have to consider the value of flexibility, and maybe then broaden it to the flexibility options. So which are the type of flexible bioenergy that can provide it, which has maybe the highest value. And this is also a topic that in Task 44 we want to tackle more in the next triennium, as this is key to place flexibility better. So I think this could be something to add here. And maybe another addition is, it depends. So which pathway we want to pursue. Of course, a lot of is with electrification, then you naturally need a lot of flexible bioenergy. But we have to look at the other components on the pathways to stay well below 2.
What about you, Daniela?
Yeah, thank you, Elina. Many things have already been said, but maybe I can again try to summarize. We see it clearly system dependent, and what are the elements for the system which need to be considered. First of all, it's the biomass potential, but I think we should also consider the actual role of bioenergy in a certain country, because typically you have already established bioenergy use, and it is an important starting point to think about having those facilities more flexible. Then, of course, it is about the potential for system integration, and this means what about other storable renewables? Tillmann mentioned the hydro question, but it's also about energy demand. If you have, for example, higher energy demand in northern countries, then heat becomes, of course, a bigger role. And then it's about energy infrastructure. For example, gas pipelines play an important role if you decide if it's more the gas or the liquid part. However, I also see that in the longer term, gases and liquid carbohydrates play an important role, not so much only for the energy system, but also to serve other aspects, other decarbonization aspects, like in chemistry, for example.
Okay, thanks. Further, let's take the results of our last poll question, which was about the most important next steps or cornerstones to unlock the potential of flexible bioenergy. And it seems that half of the votes goes for implementing appropriate support schemes. And this is actually what we are also going to work further in our next triennium in the coming years at Task 44. The rest of the answers are quite even. Less votes for monitor and share best practice examples. Those are what we are aiming to provide during this year and next year. And we believe that if we can describe the role of flexible bioenergy and what it can provide in certain well-defined conditions, maybe that will help also, for example, other markets and countries to follow the examples that are most suitable for them. So let's see how that will go. Then I will hand over to Jaap to continue with the questions from the Q&A box.
Thank you, Elina. Well, clearly, several questions in the Q&A box have been answered already by the different presenters, but I think there are some issues that are worthwhile to still to discuss. Perhaps the first one is to discuss a little bit more on CCS versus CCU. And in that respect, perhaps first, Ilka, a question to you. You grouped those two, but could you dwell a little bit on, let's say, those two individually and the importance of those two?
Well, yeah, it's I think here at the IEA, like the question went, we bundle the CCUS. I think that is just trying to reduce the amount of acronyms in the energy sector. And secondly, it's not always clear. Is EOR, I mean, it has both components of utilizing and storing. Also, if you have utilize carbon dioxide for plastics, it has this storage function as well. So I think it's not as clear, the division. And after you have captured CO2, you always have this classic question, to store or not to store. And you have to make this decision. I think it's kind of obviously also a local question. Do you have storage opportunities, geological, or is there any transport infrastructure? If you are looking at what now is happening, I think with CCUS more broadly, is that they are developing these kind of industrial hubs where a number of producers share the cost and risk of and transport infrastructure. If you had some biomass in the vicinity of that kind of, maybe you can, utilize the existing system. So maybe makes it more, you don't have to, for a standalone biomass plant, be on top of a underground storage, geological storage opportunity. But it's still a very regional. If you don't have any storage opportunities, I think the only thing is left is to do the utilization or not. And then that depends on access to low cost, low carbon electricity. I think there is this. I think in an energy system, as long as we have fossil fuels that we can displace, they are pretty much complementary options. I mean, you can have the same impact by making the CO2 into a fuel and then displacing the fossil fuel, or storing it and kind of offsetting the emissions of the fossil fuel use in a kind of an indirect way. They have the same outcome from climate perspective. But what is the kind of distinct feature of the S is that once all the fossil fuels are pushed out from the system, there are still these residual emissions from industrial and agriculture that you just cannot avoid, you cannot displace. And that for you definitely need the S to be the negative so that you can reach the net zero. So I think that's the only thing that the U cannot do, the negative part. Otherwise, it's pretty complementary. And in this topic, I think, why we see so much interest on this, I think, is because of the net zero pledges. A number of countries have done that. And I think now they are indirectly have now committed to negative emissions as a result, I think, and that is becoming maybe as a surprise to many countries that, oh, we now need to do negative emissions. And that's an outcome of a net zero pledge.
Thank you, Ilka. Perhaps in connection to this, Christiana, you mentioned that if you want to do CCU, that may require, let's say, a more constant rate, and in that sense, maybe not so easy to combine with flexibility. But could you also translate that or try to find a way out by saying, well, perhaps you can develop applications for the CO2 that also allow this flexibility? Yes, so in that sense, in terms of a technology solution to cope with the flexibility in the production plant, and also have a flexible CCU option.
Thank you, Jaap. This is a very good comment, and maybe the next research question that you just raised. But basically, what we were trying to say with the CCU is maybe you have what Ilka mentioned, there are hubs that are established in regions where you can transport this. So you have a contract because it's linked to a certain business. So since you have a contract, you have an obligation. And based on this obligation, you can't allow to have maybe a lot of fluctuations. So this is something that you have to consider. And this is something, for example, if this is also was raised by the audience, if you read through the Drex case study, we just posted the link as well from the Biogas or BioCCS case studies. If you go to the Drax one, this is the one where it's compared. So the idea they are having is going more to CCU. And when they are doing this, they have also a hub there. This would then mean for them that they have an obligation. So that's why they're saying maybe then flexibility is not possible. But this is just thinking about it. It's not having a real practice result. So maybe going into practice, maybe there is freedom for some flexibility. But we need some more real life things happening.
Yeah.
So we would be really happy that these applications come into place.
That is clear. This is clearly a work in progress, and also in terms, I think that was good that also came out of the poll, that there is also further work needed in terms of technology options. In that respect, there were several questions concerning these technology options, and one of the questions was, what about flexibility if you use solid biofuels? And perhaps it's good to discuss that here as well. I mean, if you talk about flexible bioenergy, is it then mainly gaseous and liquid biofuels, or is there also a potential for solid biofuels? And Alexander gave an answer, but perhaps Tilman, you could also shed some light on this.
I'm actually not so sure whether the best suited person. I don't know whether Daniela wanted to mention on that.
Well, in view of technology, perhaps you could.
Yeah, in view of technology. I mean, there are combined heat and power plants which run on solid biofuels, which can actually operate in a flexible way. And what is always possible, especially if you have steam turbines or so, as a electricity production, you actually can change the ratio between electricity production and heat production. That is always possible already today. The question is whether you can then make use of the heat in that respect.
Would it also not be that, I mean, solid biofuels, of course, in itself, they may be less flexible, but for instance, if you use them and combine them with gasification, then after gasifying them.
Yeah, the gasification, I mean, that is a very nice key, and that's actually something I wanted to mention before. I hope I'm not deviating too much before Daniela can answer. But, you know, if you go actually from biomass to something which is a hydrocarbon, so that could be methane, that could be diesel, that could be actually plastics or so, then you always have that point that the biomass contains way too much oxygen compared to your product. So at a certain moment, you have to take out the oxygen from the system. And then you have two ways to do that. One is we add hydrogen and take out the oxygen as water, as water at the end, or we don't have enough hydrogen around, then we have to take out it as CO2, which means in all this production of these products, we can choose whether we take out CO2 and then it will be available for negative emissions, or we add hydrogen and we get just more product, so because all the carbon ends up in the product. And that actually allows you to even combine the two ways. And actually, when you have hydrogen available, because there's renewable electricity is cheap and is available, then you add hydrogen to the process, you get more product, and all the oxygen is taken out of the system as steam. Or you don't have, because it's maybe no wind, it's winter, no PV, then you don't do that, and then you take out the oxygen as CO2, which is then available for sequestration. At the end, I see then you don't have so much CO2 available for sequestration, what Christiana mentioned, but on the other hand, I actually have everything combined in one plant, and if there is cheap electricity, actually I make my business on producing more valuable product on cheap electricity, and in the other times I make my business based on negative emissions. Could be. Okay, yeah. Daniela, did you want to add something to this, or?
Yeah, maybe just more from a system perspective. I think so, what also Tilman said is solid biofuels are especially interesting for product flexibility. Yeah, that we can produce different products in parallel, but they are not so interesting for this operational flexibility where you need these ramp ups and downs. Alexander has clearly shown. So I think this is why we still hamper a bit with the definition of flexibility and always have all aspects in mind. And let me
okay, yeah, perhaps.
give you maybe one. I would also give you one additional answer to the question CCS and CCU and where to start, and does flexibility and CCS impediment each other. I think we have seen in Ilka's presentation, there's a big increase in biogas and especially biomethane expected. And biomethane is, from my point of view, really an interesting point where you can combine flexibility and CCS in a perfect way, because when you produce biomethane, you have this mix of biogas, which is about 60% methane and 40% CO2, and we already do today CO2 separation in those plants. We call it biogas upgrading because we want to have the biomethane, and this CO2 is more or less a pure CO2 stream, which is, from my point of view, an interesting starting point for CCU or CCS. The problem is that the plants are not so large. Yeah, so you have some problems to bring enough CO2 together, but I think this is something which really can serve flexibility, the future needs for the energy system, and also provide CO2.
Okay. Well, thank you, Daniela. Perhaps one short final question to Alexander, if allowed, Irina, if we still have time.
One short question.
Yeah. Very interesting, your presentation on these virtual power plants. I understand that actually that is standing practice at the moment already. But well, you did not dwell a lot on is that in every country, or what is the overall the status of this concept, and do you expect significant changes over the let's say during the coming period of energy transition?
Yeah, so with our VPP, we can manage more or less every production asset. So, and also we can manage the demand side. So, and in Germany, it's necessary to have a direct marketer if you have a plant over 100 kilowatt peak. So in Germany, every bigger PV plant, windmill, needs somebody who manages the asset like us. So, and if we look to Europe, we see the same development in each country. So in some countries, for example, Portugal, there's no possibility at the moment, but the EU regulation says, so in the future, every country have to introduce such a system that the energy from the renewable assets come to the market. And then you need market players who manage everything. And but we see also countries like Dubai. So Dubai, there is no market, but there are a lot of assets. So, and you need a system like a VPP to manage all these assets, to bring production and demand together, to balance the grid, and so on. And so the technology is good for to manage all these centralized assets. If we talk about market, then and market players who use such a system, then we need in different countries further developments. But with the energy transition, it comes from alone. So, for example, in Japan, there are at the moment discussions to introduce a market premium system like in Germany, and other countries will follow.
Okay.
I'm really
Thank you
sorry.
very much.
Thank
Yeah,
you. I'm really
over to you.
yeah, thank you.
Yeah.
Sorry to end the session now. So just to summarize, there would be much more to discuss, and we really see a crucial role for bioenergy. The future work will be lots around the connection of bioenergy, flexibility, hydrogen, and PEC use for sure. I want to remind you that you can find the presentations and the recording in the conference website afterwards, and we can continue this discussion in wonder.me. And also, I would like to remind you that this was the last technical session of this conference, and on Thursday there will be the closing panels, so really looking forward to see you all there. Now, a huge thanks to our presenters and of course to our audience, and also to ETA Florence and IA Bioenergy for organizing all. Thank you and bye-bye.
Thank you very much. Bye-bye.
Thank you. Bye-bye.